Okay, welcome. So my topic is going to be fluctuation-induced forces. And despite what it says in the program, it will mostly be in equilibrium. And towards the end, maybe a couple of lectures will be non-equilibrium. Okay. So what are the ingredients that you need to build this? And there are different perspectives. I'll take the following perspective that what you need is, first of all, is a fluctuating field. That's where the fluctuation comes from. What does it mean? It means you have some quantity, let's call it phi. I'll make it scalar in space. Let's make space d-dimensional. And this entity is fluctuating, which means that it is described by some kind of a probability distribution. So that's the first ingredient. The next ingredient is we have to do something with it. So we have to add some kind of constraint. And constraints can come in various forms. For example, you could decide that at some location the value of phi is 0. That would be one example. Or maybe its gradient is 0. Would be another example. Or maybe you just depress the probability by adding a term that is proportional to phi squared. So that would be another thing that you could do. So essentially, you have modified how this thing wants to fluctuate. And I'm going to assume that these constraints are due to some physical entities. So for example, if your fluctuating field due to quantum mechanics is the electromagnetic field, and we put two dielectrics in them, the dielectrics will have some kind of an effect such as this. They constrain the medium. They're physical entities, so we can move them with respect to each other. And the modification of the probability because of the constraint gets changed. So the final element that you need is some way of converting reduction in probability due to constraints to some kind of a force. So we need some kind of a relationship between a probability and a force. And in thermal equilibrium, it is easy to do. We are going to rely on the Boltzmann weight as the mimic for this reduction in probability. There could be quantum versions of reduction in quantum fluctuations that we will discuss how to convert that to some kind of a force. So whereas in equilibrium, it is reasonably straightforward, towards the end, we'll discuss that when you're off equilibrium, trying to figure out relationship between the constraints in probability and an actual physical force may not be so easy. Okay, so that's the story. So let's apply these. So we have this probability. Let's impose the constraint there are two positions that I will label by x1 and x2 at which I constrain the field to be 0. Okay? So there is now a reduction in probability. It's the probability subject to the constraint that the field fluctuates throughout space, except at these two positions where it is 0. And I'm going to simplify that, and since it depends on two coordinates indicated by w of x1 and x2. And clearly, what I need to do is to integrate over all of the variables that I'm not interested, because I'm only interested in locations x1 and x2, subject to the constraint that phi of x1 is 0 and phi of x2 is 0. Okay? Which is, of course, none other than the expectation value of the product of two delta functions. Okay. So I'm going to immediately use a very fruitful technique to convert the delta functions to exponentials. So I introduce quantities that I will call Q1 and Q2 corresponding to the two locations. And the delta function I can write as e to the I Q1 phi of x1 integrated over all of Q1 will give me the first delta function, and I will have a second delta function to impose the second constraint. And the expectation value can be taken at the level of this. Okay? Now, what you have in this quantity is something that generates moments and cumulants if I were to expand it in various powers of Q1 and Q2. And in particular, I can rewrite what is in the exponent after taking the average. To the lowest order, I will have I Q1, the mean of phi of x1, and then I will have I Q2, the mean of phi of x2, and then I will have second order terms, Q1 squared over 2, the variance of phi at x1, and the variance I will indicate by an index c. So this means square average minus the average square. If I hadn't put it into the exponent, I would have had just the second moment, but once I take it to the exponent, from the expansion of the log, I will get the subtraction that makes it into a variance. I will have a corresponding thing at the second point, and then I will have the covariance of phi of x1, phi of x2, and in principle, higher and higher cumulants. Okay? So what we are going to do, we are going to assume for simplicity, so that we don't have to deal with more complicated objects, a Gaussian distribution. And further simplify things by assuming that the average value of the field at each point is 0. Yes? Yes, exactly. Yes. So I want to impose this constraint, so I integrate over all possible locations with the delta function. The delta function picks only this condition. Okay? And indeed, then I impose the delta functions through these e to the I exponentials, and then this average is a way of imposing the constraint phi of x1 and phi of x2. Any other questions? Okay. So while I'm going to do this, at the end of the lecture, I will give you a link towards where some of the lecture notes and the material is posted, and your first exercise that is given over there is to repeat this, not necessarily assuming the constraint is that phi of x1 should be 0, but some value a, and that the average of phi of x1 is not necessarily 0, but is some other value, let's call it b. So repeat what I will be doing for the more general case and see what comes up. Okay? So what we have here, however, after all of these things, is simply an integral dq1, dq2, e to the minus q1 squared over 2, the expectation value of phi of x1 squared. Actually, I don't need to put the variance anymore since I assume that the average is 0. I have q2 squared phi of x2 squared, and then I have q1, q2, phi of x1, phi of x2. Okay, so that's what happens for this special case. Okay. Now there is a reason that I call this variable q, because I want you to start thinking in terms of a fluctuating charge. So I started with a field that was fluctuating over the space. I put some kind of constraint at x1, some kind of a constraint at x2, that it has to be 0. And we see that the reduction in probability, the weight of that probability, is also equivalent to a problem where you say, forget about the fluctuating field phi of x. Instead, think about fluctuating charge q1 and q2 that sit at these positions. And the answer can be obtained by allowing these charges to fluctuate around the average of 0 at a cost that is kind of like a capacitance. So if you have a capacitance sitting over here and you put charge on it, this is the energy cost for putting the charge, which say at kT equals to 1. That would be the cost of creating that charge, the cost of creating that charge, and that's the interaction between the two of them. So the first lesson is that there are two very equivalent perspectives. One of them is a constraint fluctuating field, and the other is fluctuating charges at the locations of the constraints. And this is a picture that comes up again and again. Any questions? Again, sort of this goes back to equivalence in electromagnetism. You can describe things either in terms of the potential that is occupying space or the charges that are the sources and generate that. Okay, fine. So in this perspective, this is Gaussian integrations over q1 and q2 that I should be able to do. And make sure I don't make a mistake. I already made a mistake. The point mistake is not that big. Really, the imposition of the delta functions requires these factors of 2 pi. So there's the 2 pi here, and there's a 2 pi here. Okay? So for the Gaussian, so what do we have here? We have 1 over 2 pi squared. When I have a Gaussian integration, I will get square root of 2 pi times the variance. So I would have square root of 2 pi times the variance if I had one variable, but I don't have one variable, I have two variables, so it will be the square of that. And what is the variance? Well, I don't have one Gaussian variable. When you have two Gaussian variables, essentially what you are dealing with is some kind of a determinant. And what we have over here, if I were to write it, is integral dq1 dq2 2 pi squared exponential of minus 1/2. I can write it as q1 q2 q1 q2 with a 2 by 2 matrix, which is these coefficients, which are simply phi of x1 squared, phi of x1 x2, phi of x1 x2, and phi of x2 squared. Okay, and so what I will get for the analog of the variance for a single variable is essentially the determinant of this object. So what I need is the determinant. Let's just call this matrix M so I don't have to write it again and again. I will have the determinant of M, and the square root essentially will come over here. Okay? Everybody sufficiently happy with this so that I can go on? Okay, so this is then 1/2 over 2 pi exponential of and I guess what I need here is a minus 1/2 minus 1/2. The determinant that is outside when I go to the exponent becomes log of the determinant of this matrix is very easy to evaluate. Phi of x1 squared, phi of x2 squared minus phi of x1, phi of x2, the whole thing squared. Okay? So I can rewrite this a little bit as 1/2 exponential of minus, take this factor outside the log, so I will have minus 1/2 log of phi of x1 squared minus 1/2 log of phi of x2 squared, and then I have minus 1/2 log of 1 minus phi of x1 phi of x2 squared divided by phi 1 squared phi 2 squared with appropriate obvious notation. Okay. So what I would like to do is to then interpret this as follows. I put two constraints on the system, and I find that as a result of putting those constraints, the probability to generate a configuration is reduced by this factor that I have over here. In the way that I have written it, you can see that that one factor only depends on object 1, one factor depends on the object 2, and another factor depends on the distance between these two objects. So what I would like to interpret this, and this is where the third element of this story comes from, I would like to interpret this reduction in probability in terms of some kind of a Boltzmann weight, which corresponds to some kind of a cost that I will call u of x1 to put the constraint in the first place at location 1 If it was a Boltzmann weight, I would weight it by KT. And the corresponding cost to put the constraint at location 2. And so these objects I will identify with the log of the variance. So essentially, I had a probability distribution that had some variance. It could explore all kinds of places. I say, no, don't explore all kinds of places. You have to be at 0. So that reduces the cost or the probability by an amount that is related to the variance. And that's where the thing comes. And then you would have this potential that depends on where these two particles come from. Okay. So essentially, we have translated these three elements: fluctuating field, a Gaussian field, constraint, the field has to be 0, equilibrium at some temperature KT, to a fluctuation induced force, let's call it V, between x1 and x2. Just because I interpret it in terms of a Boltzmann weight, the strength of this is KT, and the magnitude is given by this, minus 1/2 log of 1 minus the covariance squared between the 2 points divided by the product of the variances. Okay. So that's something that we will be using a lot. In many cases that we are dealing with, as you move these 2 points further and further away from each other, the correlation between them falls off further and further, so that at large separation, this object becomes small, and log of 1 minus small quantity, you may want to expand, and then you will get KT over 2, the covariance squared divided by phi of x1, phi of x1 squared, phi of x2 squared. Okay, any questions? Yes. Yes. No, the field is, it's like you have a surface that is fluctuating. Let's say it's like a rubber band. You take a nail and hammer it so that at that point it is exactly at 0. So at the location of the nail, the fluctuation of your interface is 0, and then there's another nail somewhere else.
The averages you compute them with respect to the measure without the constraint.
Without the constraint, absolutely. Yes, that's right. Yes. So note that I impose these constraints on top of this. It's like saying that there is a probability to throw a coin 5 times in a row to come out various sequences of head, tail, etc. What is then the probability that the third time it is heads? Okay? So you can have the full probability and then the probability that the third time is heads, and then that reduces the that is less than the full probability. Yes. Well, in this case, we have 2 particles, so we wouldn't have, it will be much more complicated. But if you had then more constraints, you would have n-body. Actually, even with the Gaussian form, it is interesting to note that if I had 3 points, I would potentially have more complicated objects because although at the level of the Q's I would only have two-body interactions, once I go to this level and take the log and all of that, I will generate all kinds of higher order interactions. Yes? I did. By the Gaussian meant that I don't need to include any of these terms, higher order terms. So if it wasn't a Gaussian, then this series that I have over here would not terminate. I would have cube fourth, all of those other things in Q, so I wouldn't be able to do the integration on Q. The reason the form of Q is quadratic and I can do the interactions is because I terminated this series with the assumption that phi is Gaussian distributed. Okay. Oh, made one more mistake here. I put the minus sign here, so this should be plus, and this should be minus. All right. So now let's calculate things, and actually henceforth we will be calculating things for the Gaussian so-called free field theory. Gaussian is synonymous with free field theory. Where the probability distribution of my phi of x is proportional to an integral over all functions phi of x. Well, actually the partition normalization would be the probability is not. Probability is exponential of minus integrate over all of space. Let's put the 1/2 in front. I will have a term that is proportional to phi squared, whose coefficient I will call c squared, and a term, and let's put a k out here, gradient of phi squared over 2. Okay. So this is the standard form of a Gaussian functional. Essentially at lowest order, you either have something that is phi squared if it is local, and gradient of phi squared could potentially be higher order terms, but we are going to stick with this. And actually, as we'll see, most of the time we'll even ignore this c. We set the correlation length going to infinite, so we have only the gradient of phi squared term. Okay. Now, here, phi's at neighboring locations are coupled to each other through the gradient squared. And in order to make things simple, it is good to go to Fourier space, where you trade your phi of x with Fourier components that I will indicate by phi tilde, depending on the wave vector q. Okay. So then the probability distribution that at the level of phi in space is coupling different locations in Fourier space becomes product of independent components q. The weight of each one of them is going to be k over 2. This gradient squared becomes q squared, and then I have c to the minus 2, and then I will have phi tilde of q squared. And I will warn you ahead of time that in principle, depending on the definition that you use for how you go from phi of x to phi of q, and the discretization, various elements should take place. In particular, I think in the notes, I use a notation where the normalization involves some factor of volume, but I'm going to typically be rather cavalier without that, and potentially from one formula to another formula, neglect including the appropriate factors of V, when I know that the final answer should either be extensive or intensive. I can then figure out whether it should have V or not. Okay? So another exercise, if you like, is to go through my notes and make sure all of the factors of V are in the right place. That would be actually a useful thing if you then let me know. Okay? So once you have done that, then calculating the various variances that I need in Fourier space is trivial, because I have that the different phi tildes are independent of each other, and the variance for one of them is given by this factor of something like v k q squared plus c to the minus 2. Okay? Once I know what the variances are in Fourier space, I can convert that and calculate what the variance between 2 points, x1 and x2, which is the quantity that I need in order to calculate fluctuation-induced forces, is in real space. Okay? So what I end up, essentially to get this, I have to do a Fourier transform, which when I go from discrete representation that I have to continuum, I will need to put these factors of 2 pi to the d. I will have e to the I q dot x1 minus x2 from the Fourier transform procedure, and then the Fourier transform of the variance in Fourier space, which is this factor of k q squared plus c to the minus 2. Okay. We note that there is an overall factor of 1 over k. And another thing that you may notice is that throughout I have been kind of neglectful for putting various factors of kt, or over here there I put on the factor of k. Turns out that once you are calculating these fluctuation-induced forces, you always need ratios of this form. So all of the k's and kt's, etc., at this level are unimportant. So it's good to know a priori what kinds of things you may not need to pay attention to. Okay, so then I have a Fourier transform that clearly depends not on x1 and x2 separately, but only is a function of the difference. This function I will call, once I have scaled out the k, and function I that depends on dimensionality, so I emphasize that over there. And to make things nicer, I put a minus sign over there too. Okay? And the reason I wrote it that way is because now you can convince yourself that if I take the Laplacian of this function, the Laplacian of this function will bring down a factor of minus q squared. That's why I put the minus there. So it will be q squared. And q squared I can write as q squared plus c to the minus 2 minus c to the minus 2. Q squared plus c to the minus 2 against this will cancel and will give me a Laplacian, will give me a delta function. And then the q squared I wrote as q squared plus c to the minus 2, so I have to subtract c to the minus 2. But c to the minus 2 against exactly the same integral as before. So I will get ID back divided by c squared. So I can either try to evaluate this function using that approach or by solving this differential equation, which is essentially the inverse, if you like, of the operator that is acting over there. And so we can do that. In the notes, this is fairly standard. I have told you how this thing behaves. And clearly, there is a characteristic length scale, this c, such that when your distance is much larger than c, you have a function that is going to be decaying exponentially. So you know that this ID of x behaves as follows. For x's that are much larger than this correlation length, it is bound to decay exponentially. And in the notes, you can convince yourself that there is a there is a power law factor which is b minus 1 over 2 that accompanies this. But for most of our work, we are going to be interested in the limit, as I said, where I set this c to infinity, so that essentially I'm focusing on the short distance regime where this is absent. And then in the short distance regime, you can see that this is really just a Coulomb potential in d dimension due to a charge sitting at the origin. Okay? And so that's something that decays as x to the d minus 2 divided by d minus 2 and some surface area, which is the analog of 4 pi or whatever. The important thing is, again, the power laws. Okay? So that's what we are going to focus on. Do you agree to accept this, or do you want me to? It is given in the notes. Okay. So I now know what the behavior of these phi x2, x1, x2, which is what I need, how it behaves for this kind of theory. And in particular, I'm going to again be focused in the limit where the correlation lengths are infinite. So focusing on this. And again, you can see that ultimately what I really need is the ratio of this object with respect to the same object calculated at locally at the same location. So you don't even need to know any of these factors over there. So let's focus on the two limits that are kind of different. If I were to look at d equals to 3, then the covariance between 2 points that are separated by a distance x, so one of them I can set to 0, it doesn't matter, it's translationally invariant, we said is going to fall off as 1 over x, which is the characteristic Coulomb interaction in 3 dimensions. Okay. I really need the ratio of this object to phi of 0 squared. And you say, oh, that's a problem, because if I set this to 0, then phi of 0 squared diverges. In all of these field theories, in order to make things manageable, we have to introduce some kind of a short distance cutoff. And so essentially, what is implicit in all of this is that there is some kind of a short distance scale. You cannot extend these objects to distances that's shorter than some characteristic length scale. And so essentially, if I want to take the appropriate limit where this object becomes a meaningful version of that, I cannot go closer in x that this characteristic spacing A. Okay? So once I impose that there exists this kind of cutoff in the theory, I sort of trade in all of the prefactors, etc., by requiring this ratio that I need to be the short distance cutoff to the actual distance that I'm looking at. Okay? So once we have done that, we get that the potential as a function of the distance between 2 points is kt over 2 log of 1 minus a over the distance squared, which for distances that are large essentially becomes minus kt over 2 a over r squared. So if my fluctuating field at the beginning was simply something like this gradient of phi squared theory, which is a mimic scalar version of electromagnetism, and I impose the constraint that the field should vanish at 2 different points, what I end up is an interaction that falls off as the inverse square of the separation. So again, you can see this you could have already seen in various things that I have written, that A over R is like the Coulomb potential. The fluctuation induced potential is going to be the square of that. It's going to be A over R squared. And this is true in all dimensions greater than 2. I say in all dimensions greater than 2 because you can see that this expression has difficulties when I go below 2, because this, rather than falling off with separation, actually grows. And the extreme version of that would be d equals to 2, d equals to 1, for which I actually maintain this correlation length. And I say that phi of x, phi of 0 is phi of 0 squared e to the minus x over c. So essentially, for one dimension, I go to this regime. I assume that there is a finite correlation length. Then my v of r is kt over 2 log of 1 minus e to the minus 2x over c, because I have to square this. And now I assume that I am in the regime where x is much less than c, so that I can start expanding this object. So this becomes kt over 2 log of 2x over c. So the one-dimensional version of the story becomes this object. And we'll spend quite some time thinking about this factor of 1/2. So you'll see that again and again. But note that these are all fluctuation-induced potentials. If I now go to the final step and ask what is the fluctuation-induced force, in say in one dimension, I will get a force which is minus dv by dx. And since this is v and has this logarithmic dependence, let's call this x. Logarithm of x, its derivatives will give me 1 over x. And so the answer is going to be kt over 2x. Okay? So the other thing that we will do later on is doing a lot of dimensional analysis. The scale of fluctuation energy I have introduced through equilibrium to be kt. If I want to have a force, force has dimensions of energy divided by characteristic length scale. And say in one dimension, the characteristic length scale is x. So I would have known a priori that the force is kt over x. It is just this factor of 1/2 that I didn't know, and I had to do this calculation to figure out. Okay? As another exercise, which actually I forgot to put in the notes. I did d equals 3, d equals to 1, do d equals to 2. Yes?
So here you said I have a fluctuating field, it has a probability distribution, I put some constraint, I compute the reduced probability distribution.
Yes.
I read this as exponential minus beta d.
Yes.
And I say that dv over dx is a force.
Yes.
Which is using a lot the fact that the probability has to be above 1 weight.
Absolutely.
Is there a more direct way to see why this would be the force exerted on x1 and x2 by the constraint?
No, because then you need kinematics. So you want to think about particles bouncing off of each other, etc. So then I can't really start with the language of a probability distribution right from the beginning. I need some kind of equations of motions and fluctuations, etc.
Are there other formulations? Don't you start from stochastic field equation?
Presumably, yes. But that's not the approach that I took. But yeah. Yes. I'm not sure I understand what you mean. Could you repeat that slowly? So you want to start with the probability distribution and then quench 2 points, but that's exactly what I've done. But that is exactly what gives rise to this. So essentially, through this calculation, so I had a probability distribution, let's say that was a function in discrete form of phi 1, phi 2, all the way to phi n. So they're all fluctuating. Now you say make phi of 3 equals to 0 and phi of 7 equals to 0. Okay? Because you put these two constraints, the fluctuations of the rest are modified. That's what you're saying, right? But that is already in this expression. If I evaluate p of phi 1, phi 2, 0, phi 4, phi 5, phi 6, 0, all the way to the end, that tells me how all of the others except these are fluctuating. So the probability functional, by definition, knows the answer to your question. Okay? Otherwise, it wouldn't be the probability functional. Yes? Okay, because I have dimensionality over here, okay? And then this expression here, you don't see dimensionality except that Q is a vector in d dimensions. When I calculate averages of that and integrate, then I have dimensionality integrated over here. So the result of doing this integration, which is a function of the separation, does depend on dimensionality. When I do the calculation, I find that the dependence on dimensionality is this exponent. Yes? There is the famous mattress effect, but indeed, fluctuations. But there, the issue is the following, that among my 3 ingredients, there was the third one, that I should be able to interpret the probability in terms of some kind of energetics and force. And for the case of the mattress, the fluctuations of the matrix before people start jumping up and down on it is not governed by some KT. So if I want to do that, then I have to go to the non-equilibrium version, which was the question that Julianne was asking, and maybe we will approach that towards the end of the lectures. Okay. Fine. What was the next thing? We did constrained probabilities. We did this dimensionality. Okay. Let me erase this part. Okay. Now let's keep this. So the prototype of the kind of thing that I'm dealing with, which I have, as I said, this is this gradient of phi squared theory is a kind of scalar version of electromagnetism, not surprisingly how the Coulomb potential shows up. But then if you think about electromagnetism and fluctuation-induced forces in 3 dimensions, you probably have never encountered something that falls off as 1 over r squared. But you probably all know van der Waals that falls off as 1 over r to the 6th. So question is, what happened over here? Well, the thing is that the constraint that you have to put, I said phi is 0, but why not have a constraint that is the gradient of phi is 0? Okay? It's another type of constraint. Now you can see that whereas phi was a scalar, the gradient has d components. And so when I look at these delta functions, they become delta functions in d dimensions. And then to impose them, rather than including 1q, I need to include d factors of q, which I will actually write as p. P1 and P2. So I need to impose vectors. So here I would have P1 dot gradient of phi, and then I would have P2 dot gradient of phi. Okay? So far, not much. I will have here P1 squared gradient of phi at the first location squared. I will have P2 squared, P1 dot gradient, P2 dot gradient, and then I would have here P1 squared gradient squared, P2 squared gradient squared. And here it becomes kind of interesting. When P1 and P2 are these objects, then they have components. So P1 has component 1 to d that I can indicate by P1 alpha, alpha running from 1 to t. P2 will have components 1 to d I can indicate by P2 beta. And then the corresponding thing that appears here is the gradient with respect to alpha of phi 1, gradient with respect to beta of phi 2. Okay. All right. So then out here, what would I have? I will have d dp1, d dp2, e to the minus p1 squared gradient of phi 1 squared, p2 squared gradient of phi 2 squared, and importantly this p1 alpha, p2 beta, grad alpha phi 1, grad beta phi 2. Okay, so let's not repeat this. ultimately, you can see that what you would need is something that is more complicated. All right. So ultimately, again, yes? Yes. The mean of the gradient does not have to be 0. Oh, sorry. The mean of the gradient itself, not gradient squared. Okay, so you would have that if I were to integrate between point 1 and point 2, let's say along a line, phi of x1 minus phi of x2 would be the integral of the gradient. If I assume that the average of phi of x1 and average of phi of x2 is 0, and the whole thing is translationally invariant, the average of the gradient has to be 0. Okay? All right. So, all right, so let's figure out what this interaction is. Essentially, what I need to do, and as I said, the coefficients are not going to be at the end of the day important. So what I need to do is to take two derivatives of some interaction that depends on distance. The distance I'm going to call x gamma. Sum over gamma is implicit, so that's r squared. To the power, what power was it? Power was d minus 2. So r squared will be to the power of d minus 2 over 2. Okay. So once I do that, the first derivative will give me d minus 2 times x beta divided by x gamma. I did something. It should be 2 minus d, right? Yeah, 2 minus d. So 2 minus d over 2, so that in d equals to 3, I will get a 1 over r. I will get here a 2 minus d. This will be x gamma to the power of d. And then I take another derivative. I will get 2 minus the x alpha x beta divided by x to the power of d plus 2. And then I take a derivative here. I will get a delta alpha beta x to the d. Okay? So that's a typical dipole-dipole potential. So in 3 dimensions, you would have the 1 over r cubed type of the dipole-dipole interaction that you have. So what you see is that essentially the reason that I chose these p's was that when I impose a constraint not on phi, but on gradient of phi, in the electromagnetic language, what I end up is having to introduce fluctuating dipoles at each location, right? So in the previous case, where phi was 0, I had these fluctuating q's. If I set gradient of phi is 0, then I will have fluctuating dipoles at each location. So essentially, these would then correspond to the cost of creating a dipole, which in 3 dimensions is usually called polarizability. And this is the interaction between dipoles that you have, which would be 1 over r cubed. Okay? So I don't know how much to go into this, but because of this vector character, if I were to do things properly, rather than the 2 by 2 matrix that I had before, I will have a 2D by 2D matrix, because the different components of this D component vector are coupled to each other. Okay? But it turns out that if you have 2 points, you can decompose the dipole into components that are along the line that is joining them, that I will call longitudinal. So I have P longitudinal 1, P longitudinal 2, and I will have independent components that are orthogonal, which in 3 dimensions there would be 2 of them, in D dimension there would be D minus 1 of them, which are the transverse components. And when you make these decomposition, this matrix immediately separates out into the component that corresponds to this and the component that corresponds to that. And you can separately calculate each one of them by itself. And I will maybe leave this as an exercise to do this. Actually, in the lecture notes that I will give, I have already done it for the case of D equals to 3. So your exercise may be to do it for general D. So what you find is that this V of x1 and x2, when you have dipole fluctuations, and I'm going to impose the condition D equals to 3, we have this kt over 2, but then we have 2 factors of logarithm that contribute from the longitudinal and from the transverse components. From the longitudinal components, what we get is 1 minus 2 a cubed over r cubed squared. So essentially, why a over r became a cubed over r cubed, you can already see from this argument. That is, the direct interaction is proportional to 1 over r. The dipole-dipole interaction involves 2 derivatives of 1 over r, so it becomes 1 over r cubed. There's a coefficient when you look at the longitudinal components, that is 2. And there are 2 transverse components in D dimension, so that's where the 2 comes from. And then you have the log of 1 minus a cubed over r cubed. In fact, it is, to be precise, minus a cubed over r cubed squared. But because of the square, it doesn't matter. And what you get is minus 3 kt in total, a over r raised to the 6th power. Okay, because the whole thing here has to be squared. Okay, so once we go from the constraint on phi that corresponded to fluctuating charges to the constraint on gradient of phi that corresponds to fluctuating dipoles, we get the fluctuation induced dipole-dipole interaction, which is the thing that is the most common interaction that we have in 3 dimensions when we have fluctuating electromagnetism, and it falls off as a over r to the 6th power. Okay? Now, this a was introduced precisely for the same reason that I had done it before, so that the value of the correlations, when I calculate them at large distance, when they become coincident, becomes equivalent to what it is at the coincident point. So that's how A is introduced. In reality, the constraint that you have when you put an object in 3-dimensional space is that rather than setting the gradient of phi to be 0, the object typically has a dielectric constant that is different from that of vacuum. And so over the extent of the object, you get something like that dielectric constant times the electric field squared. Okay? So among the constraints that I mentioned was phi equals to 0, gradient of phi equals to 0. For actual physical objects that you put into the field, electromagnetic field, it is a suppression of the gradient fluctuations by an amount that is related to the dielectric constant. But if I were to Fourier transform that, it will again look very much like this and will give me dipole-dipole fluctuations. The difference is that these coefficients, rather than being gradient squared averages, become the polarizability of the object. The cost of creating a dipole on an object depends on various shape parameters, etc. So that when you look at the full analog of this for dipole-dipole interaction, the coefficients that I have over here, rather than a to the 6, becomes the product of the polarizability of one object, the polarizability of the other object. Polarizabilities have dimensions of volume. And another exercise that I have given you in the note is to do the analogous calculation here for objects where I give you their polarizability and guide you through calculating all of this, and you come up with exactly this answer, except that this a to the 6 is replaced with the product of polarizabilities. I have another 25 minutes, is that right? Okay. Any questions? Yes. 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 The 1 over r was the direct Coulomb interaction. So if I have two charges, I have 1 over r. When I have fluctuations, induced interactions, it gets squared. And similarly here, the 1 over r cubed of dipole interactions gets squared, becomes 1 over r to the 6th of van der Waals interactions. Okay? All right. So I told you that we are going to dissect this factor of 1/2. So this is thermal FIF in D equals to 1. And I'm going to look at it by 3 different approaches. Approach 1 was indeed what we have over here. I will rewrite it, which was KT over 2 log of 1 minus explicitly including this cutoff because of the difficulties that this theory has at large distances, but then focusing on the limit where psi goes to infinity, if you like. And then this became KT over 2 log x. Did I make a mistake here? If I were to expand this, I will get 1 blah 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 plus 2x. Right. Except that I think I forgot the minus sign that goes. No, that's fine. And if here I lost the minus sign. Yes. F is minus dv by dx. Because of the minus sign, it's an attractive force whose magnitude is kt over x and has this coefficient of 1/2. Okay. So I'm going to calculate this by 3 different approaches. The first approach we've already done. The second approach is the following. So I have a line, it's in one dimension. I impose the constraint that the field is 0 at x, and it is 0 at some other location. Let's call something that I was calling previously x, I'm going to call it h. So at two locations that rather than being separated by x, they are separated by h. And the reason I do that is because we are going to be doing this multiple times in higher dimensions, where rather than having points, I will introduce barriers, which essentially says forget about this part of the space, forget about this part of the space. You have a fluctuating field between 2 points where the value of the fluctuating field is constrained to 0. So essentially, I have cast the problem in terms of a field that is confined between a space with 0 to h, having to go to 0 at the two boundaries. And I say, okay, if I'm doing statistical physics, what I need to do is to calculate the partition function just for this interval, because what is out there does not really contribute to the partition function for this interval. Partition function for this interval, I have to do a functional integral over this field phi of x, and I'm going to henceforth set the correlation length to infinite. This is dx d phi by dx squared. And again, subject to the constraint that this is in the interval 0 to h, and phi of 0 and phi of h are set to 0. Okay. All right. Now, I claim that I'm just, let's say, interested in how things behave. I'm calculating, this is also equivalent to calculating the partition function for a fluctuating string, if you like, that is fluctuating between these 2 points. I expect that there is some kind of a free energy that is going to be proportional to the length of this system. So I expect that this thing is going to grow exponentially to some kind of free energy per unit length times h, just from knowledge of things that are happening in statistical physics. One way of thinking of how you would calculate that is imagine that you were to discretize this integral, and if I were to ignore the constraint, you would say that this gradient fluctuate, etc. Integrating over the fluctuations of this spring will give me some factor multiplied by this factor. Ignoring the constraint, essentially I would have all of these factors multiplied. So indeed, if I don't constrain the endpoint, the answer is simply that. Now, what happens if I constrain the endpoint? I claim that the effect of constraining the endpoint is simply to reduce this by a factor of h to the 1/2. Okay, how do I know that? Well, I say let's go back and think about this analogy of this spring that kind of fluctuates and I don't constrain its endpoint. Okay. After I have gone a distance of the order of h in this direction and I haven't constrained it, how far has it gone in that direction? I claim it's just executing a random walk, so it should be h to the 1/2. And if I constrained it so that rather than being anywhere there, it has to be over there, I have reduced the probability roughly by this amount. Now, later on, we will be spending some time thinking about polymers. And indeed, what I have calculated is the probability of a polymer, or alternatively, a random walk to return to the origin, and we'll do this somewhat in more detail. If I didn't constrain it to return to the origin, the endpoint will have a Gaussian distribution because of the central limit theorem, and the normalization of that Gaussian distribution will have a factor of h to the 1/2, which is what has happened over there. So in principle, there could be something like this. Okay? So just from these hand-waving arguments, I know that log of z of h is going to have a part that is a constant, a part that is linear in h, and a part that is minus 1/2 log of h. Now, this part is certainly not universal in the sense that it depends on this parameter k, properties of the springs. If I were to complicate the system, this will change, but this 1/2 will not change. This 1/2 is a universal object. Okay? Now, I claim that once I have this, I can calculate a force, which is the logs, beta times force, beta being the inverse of kt, the log z by dh, and essentially it will have these non-universal parts, and then I will have a term which is minus 1/2 1 over h, okay, which is exactly this term. Okay, so that's why this 1/2 is important, because it is related to something that is universal and very nice. And you say, well, but this term is much more important than this. That's correct, but it doesn't matter if I were to have these points and move them around. From this term, I will get a factor of f, but then I lose the same factor of f from the other side of the interval. So when I'm moving something where the medium that is fluctuating is the same on both sides, these non-universal terms are not going to affect the force. Okay? So that insight is important. First of all, why this is universal, and why in higher dimensions also various non-universal terms that correspond to free energy per unit volume, surface tension, all kinds of things like that will drop out and will not be things that you need to concern yourself with. Okay? Okay, so let's do this a third way. So this z of h, I said I can write, rather than writing the probability in terms of phi in real space, I can write it in terms of Fourier space. And when I do that in Fourier space, the different modes that are parameterized by q are going to be independent. And the weight of each one of them is going to be simply phi tilde of q squared times q squared, because of the gradient. That is important. And if I'm calculating the partition function, what I need to do is to do an integration over phi tilde of q. Okay. So then I get a product over q, and again, let's write proportionalities throughout. I have a bunch of Gaussian integrations. I will get square root of 2 pi. The variance is k q squared. And so when I have the answer converted into log z of h, I have a sum over q. I have a factor of square root. The square root becomes a 1/2 when I take the log. The kq squared is in the denominator, So when I take it in the numerator, I will get a factor of minus 1/2. And I have a log of k q squared. Now, the log of k is going to give me, well, actually, maybe I will hold on a second. Now, if I'm looking at some interval between 0 and h, and the field is forced to be 0 on the two ends, the kind of Fourier modes that I need to include are things like n pi x over h for integer n, so that for x, 0, and h, I will get 0. So essentially, you can see that my allowed values of q are multiples of n pi over h. So that really, up to things that are interesting, this is a minus sum over n log q squared. I have taken square over here, gotten rid of the 1/2, and qn is 2 pi n pi over h, n starting from 1. Okay. So that's again another way of calculating the partition function. Once I have the partition function, I calculate beta f, which is d log z by dh. The h dependencies come from these factors over there. The h is in the denominator, so when I take a derivative, the minus sign cancels. Log of h, its derivative will give me a 1 over h. And then I have to do a sum over n equals 1 to however of 1. Okay. So I have to evaluate that sum. Okay. Now I claim that in a precise manner, this sum is in fact equal to minus 1/2, which will give me the minus 1/2 that we have over here. Okay. And the reason is that sum n equals 1 to n of 1 is something that's related to series of objects that are called zeta function, evaluated at minus 1, evaluated at 0, which once regularized is the same thing as minus 1/2. And what do I mean by that? Say that the sum n equals to 1 to infinity of 1 is the limit as epsilon goes to 0 of sum over n of e to the minus epsilon n. So I have inserted these convergence factors, e to the minus epsilon n. Epsilon goes to 0, I get 1 back, but now I have a sum that I can do. And so this becomes limit as epsilon goes to 0 of the first term in the sum 1 minus the ratio of successive terms in the geometric series, which I can then start to expand. In the numerator, I have 1 minus epsilon plus epsilon squared over 2. In the denominator, I will get 1 minus epsilon minus 1. So the first term cancels, and I'll start with epsilon. And then I can, in fact, factor out the epsilon. I will have 1 minus, this is a epsilon over 2, epsilon squared over 6, and so forth. And so basically, this is the limit as epsilon goes to 0. I have a factor of 1 over epsilon. Numerator is 1 minus epsilon plus epsilon squared over 2. Denominator, when I bring to the numerator, becomes 1 plus epsilon over 2 plus epsilon squared over 4. minus epsilon squared over 6. And so what I have is the limit as epsilon goes to 0 of 1 over epsilon. I have, I think I went too far. The first term was enough. I will get 1 minus epsilon plus epsilon over 2. So I will get 1 minus epsilon over 2 plus order of epsilon squared. So you can see that this object has a divergence. It had to have the divergence because clearly it's something that goes to infinity. But then the next order term, the epsilon disappears, and I get minus 1/2, and then I have order of epsilon. Okay? So buried within this sum that goes to infinity, there's a bunch of terms that vanish as this goes to 0. There's a bunch of terms that diverge, and then there is this minus 1/2 that is the one that I claim should be considered here. And I don't expect you to have agreed with this statement until I had gone through a couple of other ways of seeing where that comes about. Okay? But now that you have seen it, I will be using it. Yes. Epsilon is in principle related to a way of introducing cutoffs over here. But it is not a straightforward upper short distance cutoff, because if you do that, you will get a wrong factor. Anything else? Okay. So since I have 4 minutes, let me skip one thing that maybe I'll do afterwards. Everything that I did so far was for classical systems, but let me finish with one example, which is quantum, which is 1D quantum interval. So essentially, let's look at the same entity where I have interval of length h, where, as I said, we have these wave numbers that are multiples of pi over h if the field is forced to vanish at the two ends. Now, if I go to some quantized version of the theory of a string that is pulled between 2 points and include kinetic energy of the string, then the modes of the string can be regarded as harmonic oscillators that have frequencies omega n that are related to the speed of sound or light or whatever you have times this q. Okay? So if you were to think about a string and the normal modes of this string, when you have included the kinetic energy, they're going to be essentially things that would be singing with these frequencies. Now, quantum mechanically, you say that each one of these modes is a harmonic oscillator, and the energy of each harmonic oscillator is h bar omega over 2, and you would put 1/2 plus some excitations. So that even if you go to 0 temperature and you don't have any thermally excited system, you still have the 0-point energy, which is h bar omega over 2. So you would say that the ground state energy of my spring is sum over all of these harmonic oscillators that are parameterized by these wave numbers that I mentioned between the two endpoints. I have h bar c over 2 because I have to multiply by c to get the frequency, h bar 1/2, and then I have qn, which is n pi over h bar, n pi over h. Okay. So what do I have? I have pi over 2 h bar c 1 over h, and then I have one of these sums. Okay. Now, this sum is another one of these divergent objects, which you can regularize, and I have given the regularization fashion step by step in the notes, and it is zeta of -1 because the exponent here is 1, which happens to be -1/12, going through exactly that same procedure as before. So the energy of this oscillator will have a part that is non-universal and will be divergent, and a part that is inversely in h, which is minus h bar c over 24, and then you have 1 over h. Okay. And once you have the energy, you can calculate a force, which is the derivative of the energy with respect to the separation. And what you get here is h bar c 24 1 over h squared, and I missed the sign somewhere, so let me correct that. Oh, when I take a derivative of 1 over h, I will get a minus sign. So that's 2 minus signs. So everything is fine. So here, what I have suppressed is not thermal fluctuations, but quantum fluctuations. And the force that I get is related to h bar. H bar c has dimensions of energy times length. So in order to get a force, I have to divide by 2 powers of length. So rather than having the 1 over h that we had for thermal fluctuations, we get this 1 over h squared. And this is a typical Casimir setup that we will be exploring in higher dimensions in the next lecture. Okay?
From what I remember on diverging series,
Yes.
so usually when we define a series, we say it's the limit of the partial sum when the number of terms goes to infinity. That's how we compute a series. And when we have diverging series, we take other protocols like the Abel or the Cesaro protocols to get a convergence. Is it clear that for a physical system, that's what nature does, that this sum has to be computed using the rules that mathematicians have defined to generalize convergence of series?
I would not believe it if I hadn't gone through this step. And I have gone through analogous steps over here too. I have calculated the analog of partition functions, etc. So whenever I have been able to test it with various methods, including methods that I would believe more, I have come up with this answer. But since I have to manage everything in a short time, I have gone towards the fastest method. Yes. 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 I cannot cross it off because it's a non-universal thing, and I don't like non-universal things. That's not the right argument. The point is that if I were to take 2 points and move them with respect to each other, I will get a free energy per unit length that is non-universal in this part. But then I subtract it because I have reduced the length from the other side. So it is the subtraction of the non-universal parts that leaves the nice universal parts. But in reality, if you had a medium where the outside was different and I was trying to open it up, I had to pay the cost. So if it is like a string and I'm pulling the string and I don't have the additional string on the other side, I have to pay the cost that is the line tension to create that string. Yes?
In the classical case, in argument B, you use the diffusion
Yes.
to justify the 1/2. In the quantum, do you have some element of that kind?
Not immediately, no. Sorry. Yes. Yeah.
I'm kind of surprised that the divergence occurs in the force and not the potential.
The log is a divergent quantity also, right?
Right.
Yeah.
One other question I had was the half.
Yes.
Specifically, property of the Gaussian underlying.
Yes. Yes, that's right. That's right. Yes. And indeed, when we go to other conformal field theories, that will be the central charge of whatever field theory is. Yes? Yes. Yes. Right. Right. Yes. Right. Okay. So again, that was partly in order to do a rapid calculation. So another thing that I could have done is, rather than enforcing the condition delta of phi so that phi is 0, I required that just as the case of dielectrics, there is some term that reduces the weight of phi. So rather than requiring epsilon to be, say, infinite, epsilon to be finite. Then when I Fourier transform, when I can say represent this in the same way that I represent the delta function as an integral over a charge, I will get an additional term that would be corresponding to q squared over epsilon. Okay? But the interaction part, phi of x1, phi of x2, is not going to get modified. And as long as you again require that interaction part to merge with the local value, none of the other things will matter. And so indeed, you can do the correct calculation for dielectrics put in 3 dimension, where in the presence of the dielectric, over the volume of the dielectric, rather than having E squared, which is gradient of phi squared, you have a dielectric constant gradient of phi squared. Okay? And you go through the whole calculation with this, you find all of the power laws that I have, except that this coefficient a cubed that I had over there gets replaced by something that is related to this epsilon, which is the polarizability. Right. As I said, in principle, what this is a quantized string, and then you have 2 constraints on the this. Now, however, in reality, what I did this calculation was because I want to build up towards doing the 3-dimensional calculation of the Casimir force, where people have put mirrors and measured the force between them. Experiments exist, agreement with all of this is true. So if you like, this is an exercise towards things that are really calculable. Okay?